Let's close out this short chapter by looking at a couple of ideas from the group of Bin Wang, which also included Webster, I think, on the processes that are argued to be important for this intensification of the Northern Hemisphere monsoon system. Not everybody is bought into the idea of this global monsoon and so on. Nonetheless, there are dynamic processes associated with them. So this is the definition again that we mentioned before. This map shows more clearly the green areas where the local summer minus winter precipitation rates exceed 2 millimeter per day, and the local summer precipitation exceeds 55% of the annual total. So that's used as a definition, but you can also think of this as the back and forth of the ITCZ associated subsidence regions, so the dry regions and the monsoon regions. This seasonal contrast of summer to winter is a definition of monsoon in this case. The main argument from that paper, Wang et al. 2013, is this figure, which shows the climate anomalies associated with the Northern Hemisphere summer monsoon system circulation index, which is the shear in this big box as opposed to the little box we had seen before. So it's the V850 minus V200 millibar or hectopascal shear. That's the index of the NHSM intensity. So it is regressed to 2 meter temperature anomalies over land and SST anomalies over the ocean. Sea level pressure anomalies are shown in contours here. Obviously, cold SST anomalies associated with anomalously high sea level pressure and vice versa. But you can see this broad El Nino-like pattern, which is called the mega ENSO by this group of authors, and the wind vectors are shown here as the 850 hectopascal wind anomalies with respect to the NHSM circulation, or the vertical wind shear index for 1979 to 2010. And then there are arguments that this interhemispheric monsoon has predictability out to a decade and so on. So this difference of this triangle and this region here is called the mega ENSO, and then correlations are sought between them. So the circulation index and the mega ENSO are correlated at very high 0.77, which is quite remarkably high, but larger the averaging area, larger the correlation in some sense in these cases. And the vertical, monsoon index, and the AMO, the Atlantic multi-decadal oscillation, which I will show in the next slide, also has a reasonably high correlation that's statistically significant at some 95% confidence level of 0.24. And the of course the interhemispheric temperature contrast. So you can see here there is a asymmetry in the warming of the northern hemisphere and the southern hemisphere. So there is a hemispheric temperature contrast setup, which also has a strong correlation with the monsoon index at 0.63. Okay, so the merged era and era interim reanalysis data were used here. So those are the two that are used to create this long timescale correlation from 1958 to 79 and 79 to 2011. So these are argued like the lower surface processes are seen to be important for creating this monsoon intensification in the northern hemisphere. Of course, it doesn't say what is the cause and what is the driver necessarily by just looking at the correlations. Causality has to be figured out, but obviously the El Nino pattern and the warming contrasts could together explain the hemispheric monsoon. If you remember in the first chapter, we looked at zonally averaged total precipitation and found that the hemispheric rainfalls are not that different despite the differences in the amount of land on in either hemispheres, and the idea that ITCZ is to the north because of either the land being more on the northern hemisphere, low heat capacity, more warming able to pull the ITCZ, or the other idea of John Marshall that the ocean is transporting heat across the equator as a part of the meridional overturning, and ITCZ acts as the energy equator and has to be in the north to be able to transport balancing energy across the equator into the southern hemisphere. So all those together here can be used to explain this hemispheric monsoon that we see here. And as we said before, those are consistent with the Walker and Hadley cell intensification, which are in contradiction with some of the arguments made by Soden and Held and Vecchi and so on. So there are many papers showing that in fact the trade winds have intensified in the last few decades, which explain why the Eastern Pacific has been in a colder or less warming pattern than the West, and why the excess heat taken up in the Pacific is being driven into the Indian Ocean via the Indonesian through flow. So all these are related. The other mode that's brought up here in terms of the correlation with the intensity of northern hemispheric monsoon, north hemispheric monsoon, is the Atlantic multi-decadal oscillation SST pattern, as opposed to the NAO, which is explained as the pressure difference, for example, between Azores high and Icelandic low, or this tripole pattern that is often referred to. It is a monopole across the entire North Atlantic, and it has a multi-decadal time scale, as you can see here. Relatively small, but persists for multiple decades, and it is also argued that in this last period the global warming is associated, or at least is got a contribution from the positive phase of the Atlantic multi-decadal oscillation as well. This phase shift happened around 1995, and there are many other connections made that for example, the change of the AMO sign here resulted in decoupling the ENSO teleconnections in some regions like the North Atlantic, Barents Sea, and so on and so forth. So these are called oscillations, but obviously you have too little data. The length of the time series is not long enough to derive too many fundamental processes, and there is a paper by Amy Clement, Mark Kane, and others arguing that ocean may not be a important player in this, so it may be just a thermodynamic mode or the atmospheric mode, and still the scale selection of these things is not so obvious. Even there are nice papers by Arno Chaya and John Marshall and so on arguing what role the ocean may or may not play in picking these patterns. So it's the same for things like Pacific decadal oscillation. So we have modes like El Nino, Indian Ocean dipole, Atlantic zonal mode or Atlantic Nino, and so on. And the debate over the Indian Ocean dipole, for example, continues as to whether it's really a dipole or whether it's really independent of El Nino, and so on and so forth. So you keep finding these relations, and you have to explain them in terms of assuming if AMO is given, then the intensification of the northern hemisphere monsoon can be explained with a contribution from AMO. And you can see that if this entire hemisphere is warm, then you would expect the hemispheric contrast to contribute to the cross-hemispheric moisture transport and potentially also the monsoon that we are looking at here. Remember that this is very much a land-ocean contrast here, even though once the convection gets set, it's able to pull the moisture across the equator, and in fact land is colder during the monsoon season. It's the monsoonal heating in the atmosphere that can drive cross-equatorial flows and so on. So this gives you a sense of the change in the global tropics, and there are other nice review papers arguing about the relations between the modes. There are more and more papers showing that the Indian Ocean warming, which is going much faster than the other oceans, is in fact feeding back to the anthropogenic the response of the Pacific Ocean to anthropogenic forcing or greenhouse gas increases and other kind of human activities that impact climate. And they also shown that the Indian Ocean warming is also affecting the Atlantic meridional overturning circulation, which relates to deep water formation in the North Atlantic and the strength of the overturning circulation. Remember that the global warming shows a warming hole in the North Atlantic where the deep water formation happens. This may or may not be a good thing. Recent papers argue that Atlantic meridional overturning circulation is the slowest in a very long time, probably many tens of thousands of years or so, and that could be related to, for example, glacier melt, Greenland glacier loss, freshwater input. Nonetheless, how does the Atlantic meridional overturning relate to the AMO, and how then that will feed back to the tropics and the Walker and Hadley cells, as well as the rate of warming of the atmosphere, expansion of the oceanic warm pool, convective heating, and so on and so forth. So many related components, not really definitive answers, but many evidences of how tropics are changing, and obviously this is key to understand how future projections can be interpreted and whether they are reliable, and so on and so forth. Okay, so that concludes this chapter, and then we'll conclude the course with the next chapter, where some summary of the ideas we have discussed throughout the chapters is given. Okay, let's leave it here.